Gas absorption is the transfer of solute material from the gas phase to the liquid phase. It is the removal of one or more pollutants from a contaminated gas stream by allowing the gas to come into intimate contact with the liquid that enables the pollutants to become dissolved by the liquid. Desorption or stripping is the removal of solute from a liquid mixture by contact with gas. The gas may be bubbled through the liquid, or it may pass over streams of the liquid arranged to provide a large surface through which the mass transfer can occur. The liquid film in this latter case can flow down on the sides of columns or over packing, or it can cascade from one tray to another with the liquid falling and the gas rising in the counterflow. An example of gas absorption is found in hydrogenation of oils, in which the hydrogen gas is bubbled through the oil with which it reacts. Generally, there is a catalyst present also to promote the reaction. The hydrogen is absorbed into the oil, reacting with unsaturated bonds in the oil to harden it. Another example of gas absorption is in the carbonation of beverages. Carbon dioxide under pressure is dissolved in the liquid beverages, so that when the pressure is subsequently released on the opening the container, effervescence occurs. An example of desorption is found in the steam stripping of fats and oils, in which steam is brought into contact with a liquid fat or oil, and undesired components of the fat or oil pass out with the steam. This is used in deodorizing of natural oils before blending them into food products such as margarine, and in stripping of unwanted flavors from cream before it is made into butter. The equilibrium conditions arise from the balance of concentrations of the gas or the volatile flavor between the gas and the liquid streams. Gas absorption equipment is designed to achieve the greatest practicable interfacial area between the gas and the liquid streams, so that liquid sprays and gas bubbling devices are often employed. In many cases, a vertical RF trace is so arranged that the liquid descends over a series of perforated trays, or flows down over ceramic packing that fills a tower. A common apparatus used in gas absorption and certain other operations is the pack tower, an example of which is shown in the figure. The device consists of a cylindrical column or tower equipped with a gas inlet and distributing space at the bottom, a liquid inlet and distributor at the top, gas and liquid outlet at the top and bottom respectively, and a supported mass of inert solid shapes called tower packing. The inlet liquid, which may be pure solvent or a dilute solution of solute in the solvent, and which is called the weak liquor, is distributed over the top of the packing by the distributor, and in ideal operation, uniformly wets the surfaces of the packing. The solute containing gas or rich gas enters the distributing space below the packing and flows upward and through the interstices in the packing countercurrent to the flow of the liquid. The packing provides a large area of contact between the liquid and the gas and encourages intimate contact between the phases. The solute in the rich gas is absorbed by the fresh liquid entering the tower, and dilute or lean gas leaves the top. The liquid is enriched in solute as it flows down the tower, and concentrated liquid, called a strong liquor, leaves the bottom of the tower through the liquid outlet. The formulas for calculating the gas and liquor streams concentrations are as follows. For the interconversions between dry and wet bases, the following formulas are used, in which capital letters are designated for dry bases and small letters for wet bases. From the gas absorption diagram, the following equations are obtained. The following are the examples of the graph of absorption and stripping operations. The sources of equilibrium data are the following: experimental data, Rolle's law, and Henry's law. Constants for Rolle's law and Henry's law can be obtained from the Paris Handbook or from other unit operations textbooks. To calculate for the absorption and stripping factors, the following formulas are used. Theoretical stages for an absorption tower is calculated using this formula.
Hi, I'm Al. Today, we are going to solve problems about gas absorption. Our first problem comes from the Chemical Engineering Reviewer of MRII. The problem says, the mole fraction of solute entering a gas absorber is 0.25. If the percentage recovery is 75%, then the mole fraction of the solute leaving the tower will be. This is a simple material balance problem, but we can solve it in different ways. We are given the initial mole fraction of our solute, which we call Y1, which has a value of 0.25. Also, we are given the percent recovery, which is 75%. We are required to solve for Y2, which is the mole fraction of the solute on the effluent gas. To solve for our Y2, we must divide the moles of solute remain to the moles of leaving gas. And we know that the moles of solute remain is equal to the original moles of solute minus the moles of solute recovered. While for the moles of leaving gas, we have the moles of solute remain plus our moles of solute free gas. For us to solve for Y2, we must know the values of these four variables. First, we will convert our wet basis concentration to the dry basis. To solve this, we will just divide Y1 to 1 minus Y1, which is 0.25 divided by 1 minus 0.25. Solving for this, we will get a value of our big Y1, which is 0.3333. Now, let us take a look to our dry basis concentration. We have 0.3333 moles of solute per 1 mole of solute-free gas because we are on a dry basis. Therefore, we can assume that our moles of solute-free gas is only 1. While 0.333 moles is our value for the original moles of solute. We have our value for the original moles of solute and the moles of solute-free gas. The remaining values that we must get are the moles of solute recovered and the moles of solute remain. But we know that the moles of solute remain is related to the original moles of solute and the moles of solute recovered. Since we already have this value, we can only get the moles of solute recovered and we can already have the value of the moles of solute remain. To solve for the value of the moles of solute recovered, we will only multiply the original moles of solute to our percent recovery, which is 0.75. It is 0.3333 times 0.75, which is 0.25. For the moles of solute remain, we will just subtract the moles of solute recovered to the original moles of solute, which is 0.3333 minus 0.25, which has a value of 0.0833. Now, we have the values of the four variables that we are looking for. We will just substitute the values we have computed to the formula. We have 0.3333 minus 0.25 all over 0.0833 plus 1, which is equal to 0.0833 all over 0.0833 plus 1. And now, we have our value of y2, which is 0.0769. Using mass balance is quite too long for us to solve. For easier calculation, we provide a formula which is big Y2 is equal to big Y1 times the quantity of 1 minus the percent recovery. For our problem, we know that the big Y1 has a value of 0.3333. So we multiply it by 1 minus 0.75. We have 0.3333 times 0.25 and has a value of 0.0833, which is our dry basis concentration of our effluent gas. We will just convert this value to the wet basis concentration to get our final answer. We will just divide big Y2 to 1 plus big Y2, which is 0.0833 all over 1 plus 0.0833 and has a value of 0.0769. As we can see, our final equation in this calculation is the same as what we've done in the previous method. Therefore, we can conclude that this formula can solve this particular problem. Upon checking the problem, we can see that we have arrived on the correct answer. Congratulations! Our second problem comes from the unit operations book of Jean Coplis. The problem says, a gas mixture at 2.026 times 10 to the 5th Pascal total pressure containing air and SO2 is contacted in a single-stage equilibrium mixture with pure water at 293 Kelvin. The partial pressure of SO2 in the original gas is 1.52 times 10 to the 4th Pascal. The inlet gas contains 5.70 total kilogram mole and the inlet water 2.20 total kilogram mole. The exit gas and the liquid leaving are in equilibrium. Calculate the amounts and compositions of the outlet phases. Use equilibrium data from figure 10.2-1. This problem will also use material balance, but in this case, we will solve using the liquid and the gas streams. This diagram can represent our problem is given and unknowns. This is our gas stream and this is our liquid stream. Our entering gas has a total pressure of 2.026 times 10 to the 5th Pascal, while the partial pressure of SO2 is 1.52 times 10 to the 4th Pascal. The amount of this entering gas is 5.70 kilogram mole. The mole fraction of the solute in this feed is unknown. For the entering liquid, we have pure water at 293 Kelvin. Since it's a pure water, we can say that the concentration of the solute in this case is 0. The amount of this entering liquid is 2.20 kilogram mole. We are to find the amount and compositions of our leaving gas and our leaving liquid. First, we will get L prime because we will use it on our overall solute balance. It is equal to L2 times 1 minus X2. But we know that X2 has a value of 0. So, L prime is equivalent to L2, which has a value of 2.20 kilogram mole. we will find the value of our small y1. We know that the mole fraction is proportional to the partial pressure. Therefore, we can compute y1 by dividing the partial pressure of the solute to the total pressure of the gas, which is equal to 1.52 times 10 to the 4th Pascal divided by 2.026 times 10 to the 5th Pascal. Calculating this expression, we get the value of our small y1, which is 0.075. We need the dry basis concentration for our OSB, so we convert this value to the dry basis. We will just divide 0.075 to 1 minus 0.75 because this is our formula for the conversion. Calculating this, we have the value of our dry basis concentration y1 0.0811. We can also compute for the V prime by multiplying V1 to 1 minus Y1, which we already get the value. V prime is equal to 5.70 kg mole times 1 minus 0.075. And we will arrive to an answer of 5.2725 kg mole. We are about to find the value of the concentration of the solute on the living liquid using Henry's law, since it is stated on the problem that the living gas and liquid are in equilibrium. We have a relationship of Pa is equal to 29.6 XA for SO2 at 293 Kelvin. XA is our mole fraction of SO2 in liquid phase, while Pa is the partial pressure of SO2 in gas phase in atm. Using the relationship we get from Henry's law, we can derive an equation relating Y2 to X1, or the concentration of the solute on the gas and liquid phase. From here, we can divide this relationship by Pp, which is given as 2.026 times 10 to the 5th Pascal. But we must take note that from Henry's law for SO2 water system, the pressure given is in atm. Therefore, we must convert units before we proceed to calculations. Pa over Pt is Y2. And 29.6 X1 for the liquid phase, all over 2.026 times 10 to the 5th Pascal. But as what I've said earlier, we must convert this to atm before calculation. We have a conversion factor which is 1 atm is equivalent to 101.325 Pascal. Calculating this equation, we have the value of our Y2 as 14.80365 times X1. We can use this relationship to find our unknown values. We now proceed to our OSB, or overall solute balance. It is V prime times quantity Y1 minus Y2 is equal to L prime times quantity X1 minus X2. We must take note that these concentrations must be on dry basis. We have the value of our V prime, which is 5.2725 kilogram mole, and we also have our value of y1, which is 0.0811. We can compute for y2 using the formula y2 is equal to small y2 all over 1 minus small y2. But remember that we have gotten a relationship of y2 to our x1. Therefore, our y2 on dry basis is equal to 14.80365 x1 all over 1 minus 14.80365 x1. Our L prime is 2.20 kilogram mole. Since our entering liquid is pure water, x2 is 0. So we will just multiply it by x1. We must take note that this x1 is different from this because this is on dry basis while this is on wet basis. Therefore, we must convert this using the conversion small x1 all over 1 plus 1 x1. We have our balanced equation with only one unknown, which is x1 or small x1, which is the mole fraction of solute on the living liquid. We can use any algebraic methods to solve for this variable. Upon calculation, we will arrive at a value of 0.004947. Since we already have our value for x1, we can solve for y2 using the relationship we got from the Henry's law. We can compute for y2 by multiplying 14.80365 by 0.004947, and we will arrive at a value of 0.07324. Now, we will calculate for the L1 or the amount of the living liquid. From our formula, L prime is equal to L1 times the quantity 1 minus x1, we can derive the formula for L1, which is L prime all over 1 minus x1. Substituting our values to this formula, we will get 2.20 all over 1 minus 0.004947, and we now have the value of our L1, which is 2.2109 kilogram mole. Lastly, we will solve for our V2, or the amount of gas leaving the system. From our formula of V prime is equal to V2 times quantity 1 minus Y2, we can derive the formula for V2, which is equal to V prime over 1 minus Y2. We will substitute our values and we will get an answer of 5.6892 kilogram mole. Let us take a look again to our problem. We can see that the values of the correct answers are the same as what we have calculated. Congratulations! Our third problem is also from the unit operations book of Jean Coplis. A tray tower is to be used to remove 99% of the ammonia from an entering airstream containing 6 mole percent ammonia at 293 Kelvin and 1.013 times 10 to the 5th Pascal. The entering pure water flow rate is 188 kg of water per hour meter squared, and the inert airflow is 128 kg of air per hour meter squared. Calculate the number of theoretical trays needed. Use equilibrium data from Appendix 8.3. This problem is almost the same as our last problem, but for now, we are to compute for the number of theoretical trays. This is our diagram for our problem. Again, this is our gas stream and this is our liquid stream. Our entering gas has a wet basis concentration of 0.06 at 293 Kelvin and 1.013 times 10 to the 5th Pascal. The amount of the inert air is 128 kilograms per hour meter squared. The entering liquid is a pure water at 188 kilograms per hour meter squared. Again, our entering liquid is a pure water, so our concentration of the solute is 0. Like the second problem, the concentration and the amount of the effluents are unknown. Again, we will get the values for our overall solute balance. First, for the Y1 of dry basis, we will use the formula for conversion and we will get 0.06 over 1 minus 0.06. We have the value of our dry basis concentration for Y1, which is 0.0638. Since we are given our percent recovery, which is 99%, we can compute for Y2 using the formula we used in problem number 1. So the value for our Y2 on dry basis is 1 minus 0.99 by 0.0638. The value of our Y2 on dry basis is 0.320. Next, we will get our Y2 on wet basis by using this conversion formula. We will get 6.3830 times 10 to the negative 4 over 1 plus 6.3830 times 10 to the negative 4. Our value for Y2 on wet basis is 0.00063789. We can now proceed to our overall solute balance. From our balance equation, we know that we have a value of 128 kg of air for our B prime, 0.0638 for our big Y1, 6.383 times 10 to the negative 4 for big Y2, and 188 kg of water for our L prime. Our L prime is 188 kg water because our entering liquid has a concentration of solute which is 0. Since the entering liquid is pure water, our X2 is 0. We have one unknown in this equation, and it is X1 on dry basis. We must be careful before proceeding to calculation because we have an inconsistency in our units. This 128 is in kilogram air, and this 188 is in kilogram water. Therefore, for us to get the right value for our X1, we must convert these amounts in mole. We will just divide our amounts by their molecular weight. The molecular weight of air is 29 kilograms per kilomole, while water has a molecular weight of 18 kilograms per kilomole. We can cancel kilogram, and we now have kilomole units for both air and water. Calculating our value for X1 on dry basis, we have 0.0267. Next, we will convert this value on wet basis. We already know the formula for the conversion on dry to wet basis. Therefore, we will arrive at a value of 0.0267 divided by 1 plus 0.0267, which is equivalent to 0.0260. We already have calculated the operating values. Now, we will get the equilibrium values for the calculation of the theoretical trace. We will use Appendix 8.3-22 for the data for the ammonia water system. This data relates the concentration of solute on the liquid phase and the concentration of solute on the gas phase. We already have calculated the effluent concentration of the liquid, which is 0.0260, which is in between the values 0.0258 and 0.0309. Corresponding these values are 0.0197 and 0.0239, which are the values for the Y. We can also see from our equilibrium data that at zero solute concentration of the liquid stream, we have zero solute concentration of the gas stream. We now have our equilibrium values. Asterisk indicates that the values we have are in equilibrium. Y1 asterisk is the solute concentration of the gas at x1, while Y2 asterisk is the solute concentration of the gas at x2. We have two ways on solving for the theoretical trace. First, we will use the analytical method. The formula for the NTO using analytical method is log of y1 minus y1 asterisk all over y2 minus y2 asterisk over log of y1 minus y2 all over y1 asterisk minus y2 asterisk. We already have the values of these variables. Substituting it on the formula, we will have the value for our NTO, which is 3.865 trace. You can also calculate NTO using graphical method. We will just plot the equilibrium line and the operating line. Equilibrium line can be obtained using datas or can be obtained using Henry's law. For our operating line, we will just plot x1, y1, and x2, y2. Once we have our operating line and equilibrium line, we will form triangles like this. From the first point of the operating line, we will connect it to the equilibrium line to the right. Then, we will connect it again to the operating line upward. The cycle continues until we cannot anymore form a triangle. Then, we will count the upper triangles we have drawn, and that value is our NTO. Now, we will solve the number of theoretical traces using the graphical method. First, we need a graphing material. In this case, I used a graphing paper. The red line represents the operating line, and the black line represents the equilibrium line. For the operating line, we have our point x1, y1, and x2, y2. To plot the equilibrium line, we use the data of the ammonia water system that we have shown earlier. Now, let us draw our triangles. As you can see, we formed almost 4 triangles. The fourth triangle is almost 80% of a whole triangle. Therefore, we can account that the theoretical trace is 3.8. Let us take a look once again to our problem. As you can see, the exit concentrations that we calculated match the correct answers. Also, the number of theoretical trace we have obtained using analytical and graphical method is the same as the final answer. Once again, congratulations!